Charles giving his final lecture on degeneration. Degeneration in rational maths. Thanks very much, Charles, and thanks for all the other lectures as well.
Yeah, it's going to blow up. Okay, so the aim today is to give the proof by G and Chi of Macmillan's rigidity theorem, which states the following. So the only non-isotrivial, isospectral, algebraic, family of rational map of a fixed degree D is the family of flexible lattice map. In fact, there are probably two, so okay, there. Family of flexible lattice map. Okay. Okay. So so the original proof relies on Thurston rigidity, and so here we'll try to use non-Archimedean degeneration. Okay. So first, I need to explain a lot of words. So what is an algebraic family, isospectral, non-isotrivial, and so on. So this is what I'm going to do. So last time I discussed the family of flexible lattice maps. So no one agreed with my formula. I checked on, and I think it was correct.
Yeah, I checked also. It was just conjugate by 1/z to the ones, but yeah, sorry.
So what is an algebraic family? Okay, so here is, in fact, algebraic family parameterized by a curve. So you fix an algebraic curve. So here we're working over C, right? So, it's smooth. So C is going to be, so you can look at the unique completion. So the unique compact complex, a compact Riemann surface, such that C is a complement of C bar, and C infinity is going to be a finite set. And so an algebraic family parameterized by C, it's the FT, G and C. So it's a set of a rational map, so P of T over Q of T, P of T and Q of T of two polynomials with coefficients that are regular maps on these algebraic curves. So if you don't like this, it's another way to state this. There are holomorphic functions in the Riemann surface attached to C that are meromorphic at any point in C infinity. Okay. So when you have something like this, then you have a natural, so you can consider the product a variety, the Riemann sphere cross C, and then you have a natural dynamical systems over the base, which is defined by f of z comma t is ft of z comma t. Okay. So this map is going to be, so it's holomorphic, but it's also algebraic. And so you can extend it to C bar. So let me put C bar here. And then the map is no longer holomorphic, but it's going to be meromorphic or rational. So above points inside C infinity, you have, so the picture is like this. If you take a point, so this is a purely local picture. Let's say P is in C infinity. So you have your map F. It's going to be a holomorphic. So the restriction is going to be holomorphic of degree D on any fiber except above P. And if you extend like this, you might have a finite set of exceptional points of indeterminacy. When I say it might or might not, but in general there. Okay. And so the restriction of the map to this fiber above a point in C infinity might be constant, might be of lower degree, anything. Okay, so now isospectral. So isospectral means that the multipliers of any periodic points are constant. Okay, so a way to formalize this. Yoo-hoo. So you pick an integer, and then you look at inside this product variety. So this is going to be inside V1 cross C. So yeah, sorry. So as above, Ft is going to be an algebraic a family of rational map of fixed degree. And so you can look at per n. This is a set of pairs such that Fnt of Z is equal to Z. Okay, so this is a two-dimensional algebraic variety, and this is an algebraic curve. Could be singular, and its projection to the base is finite to 1. So in fact, if you count with the right number of multiplicity and so on, the projection is d to the n plus 1 to 1. Okay? Okay, and so on this curve, you have the multiplier function. Let me call it mu n. Which to any pair of points is attaching the derivative of the nth iterate of that point. So this is a multiplier function. Okay, and to be isospectral means that all these functions are constant. Okay, so locally constant. So isospectral for all n, mu n. Okay, so for, maybe I should say this way, for any reducible component of per n, d of per n, the restriction of mu n to d is constant. Okay, I say irreducible could be connected component, right? Okay, so we heard quite a lot about stability of a dynamical system. So just a remark. So I'm not going to define this very precisely, but to be isospectral is equivalent to say that the family is stable. So a family is stable if you don't see any periodic points that whose multiplier is crossing the, let's say, the unit circle. And so here the multiplier function are algebraic, and so either they are constant or they have to cross the unit circle. Okay. So if you don't like isospectral, you can replace by stable family. Okay. So what's next? Yeah, flexible lattice family. So I'm not going to write down again. So I defined this last time. So I just wanted to make one remark. One observation. So we looked at the family, Macmillan family, Ft of Z, Z squared plus T over ZQ. And so this family is not, so this is Macmillan family. It's not in the same paper, right? So, and this is not a flexible lattice. But then there is something interesting here is that if t goes to 0, so it's an algebraic family, right? Parameterized by t. So a priori it could be in C, but when t is equal to 0, the degree is dropping down to 2. So here the parameter space is A1 minus 0. So if you look at what's happening close to 0, this is what we described last time, and we check that the non-Archimedean dynamical system has has no repelling classical periodic points. And in fact, this is equivalent to say that if you look at all the components of per n plus pi, and you look at the multiplier function, then the multiplier function is going to extend holomorphically. So let me draw. So here is t close to 0. And then you have this curve per n. Okay. And in fact, what we check is that so it has no repelling classical periodic orbit, which means that the multiplier is a holomorphic function which extends at 0. And so in particular, mu n for any n is holomorphic near 0. So it stays bounded, right? So prove this, yeah, well, it's an observation. So mu n extends holomorphically near 0. So what it says, this result, what it says is that, okay, so here we have a family that's not parameterized by A1 minus 0. At 0, you see nothing. No one is exploding. So what it says that when you go to infinity, in fact, it has to be that some periodic points, some multipliers are exploding. Okay. So you can actually prove this, right? So consequence, there exists some periodic points whose multiplier explodes near t equal to infinity. Okay, so I think I defined all terms here, and so now I would like to. Do you want me to be more specific on this, or it's fine? No, okay. Serge said it's fine, so it's.
Laura was confused with your symbol.
There exists.
Yes, you underline
P
it.
and Q. Okay.
Consequence.
No, that's fine. No.
Okay. So now I'd like to give a sketch of proof, the proof by G and Chi. And so to do that, the first thing I need is to exploit the fact that the family is parameterized by an affine curve, and that the moduli space of rational map is affine. So let me spend like a couple of minutes to explain why this is the case. So this is where we exploit the fact that the family is algebraic. Okay, so what is the red D? So D is at least 2. Red D, this is a space of all rational map of degree D. So if you fix homogeneous coordinates on the Riemann sphere on P1, then you can write any rational map in homogeneous coordinates by, so it's going to be determined by two homogeneous polynomials of the same degree D without any common zeros. So yeah, my favorite notation. Okay, and so if you look at the coefficients, let's say AI for P and BJ for Q. So you have 2D plus 2 coefficients in total, but then you're looking at homogeneous coordinates, so you can always multiply by the same constant and you get the same. So this is something which lives in P 2D plus 1 over C. And then you have to understand what is this condition that the two polynomials have no common zeros. And so you can, a nice way to do that is to consider the homogeneous resultant. The resultant of P and Q, and the fact that they have no common zeros is saying that this homogeneous resultance is non-zero. So this is, I'm not going to write down the formula. So this is a polynomial. It's homogeneous polynomials in the AI and BJs of degree 2D. And so if you want, the rad D can be identified by two Zariski open set in this projective space. And its boundary is exactly the locus where this function, this degree 2D function is vanishing. Okay. So what is an algebraic family? It's exactly a map from C to rad D. That's it. Okay, but then you know that you want to identify two rational maps that are conjugated. So you're going to look at the action by conjugation of the group of Möbius transformations. So phi acts on F, maybe on the left, so phi F, phi minus 1. And so you're interested in the set of conjugacy classes of rational map of degree D. So there are first thing by Hilbert. Okay, so rad D, being a Zariski open set, is determined by this ring of regular function. So it's the spectrum of the ring of regular functions. And so the first thing that you can do is to look at regular functions on rad D that are invariant by the conjugacy action. So you look at algebraic functions that are invariant by conjugacy. And there is a theorem by Hilbert that says that this is still finitely generated. So you can look at, it defines an algebraic variety that you're going to define as being MD.
You're actually using that to remove hyperspace. It's not just as a risky open.
Yeah, and it's easier to see them also.
Why?
I mean, if you remove the point from projective space, it's not actually right.
Yeah, sure. Yeah, sure. I didn't say fine. Sorry. Yeah. So sorry. Yeah. You're right. Okay, and then there is a theorem by Silverman that is using GIT theory, geometric invariant theory. So this is Hilbert, this is Silverman. That tells you that over C, in fact, the points here are canonically in bijection with a set of conjugacy classes. Of rational map of degree D. So MD, this is a moduli space, if you want to have a rational map, and you have a natural map from rad D to MD, which stands F to its conjugacy class. I'm going to write it as CL. Okay, so I know a lot of you know a lot of things about this, but let me just recall what is it. So the geometry of MD is quite interesting. So when D is equal to 2, it's known to be, M2 is known to be isomorphic to affine plane. So this is a theorem due to Milnor and Silverman. And when D is greater or equal to 3, then the situation is a bit different, but still there is a theorem by Alan Levy saying that MD is rational. So it's by, if you can compact phi, this is by rational to P. So it has dimension 2D minus 2. So it's birational to P 2D minus 2. It's quite a non-trivial theorem, and I don't think that in higher dimension this is known. And also there is so it's a space when D is at least 3. It has singularities coming from the fact that a map might have a non-trivial centralizer, and this single, in fact, it's a fact that so these singularities are quotient singularities, and the locus is non-empty. So when D is at least 3. So this is a theorem by Myasnikov, Stout, and Williams. Wilson. Okay, so MD is affine. And so you can, if you want, you can realize it as a subvariety in some big affine space. And the affine space you can compactify in the projective space and look at the closure of MD. So what it means that I'm going to choose an arbitrary projective compactification. So there are a lot of works, in particular by Laura, on trying to find a good compactification of that space. Here, I just take a random projective compactification. Okay, and so when you have an algebraic family, so remember that you have this map, from C to rat D, and so it goes down to, you can look at the class map, to MD. So this is regular. And then you can extend it to the closure, right? Since it has dimension 1. Okay. And then, so you have 2 cases. Now I realize that I didn't explain this non-isotrivial. So when you look at this map from C to MD, so either it is a constant, and then so that means that if you take any 2 points in C, in fact, that define the same conjugacy class, so they are conjugated by some element, some Möbius transformation. So this is what I call isotrivial, or it is not. And then, so look, so you have, so this is MD, you have the boundary, so MD bar minus MD, and you have your curve, and your curve is, C bar is complete, and so it has to touch the boundary, cannot be contained in the affine part. So it is not, which implies that there are some points P in the boundary C infinity, such that, let me call CL of P, belongs to the boundary. Okay, so you have to, when you look at the image of C inside the moduli space, have to touch the boundary of that moduli space. So in other words, it has to degenerate. In the moduli space. At least 1 point. Okay. So since in this statement I excluded the isotrivial families, I know that there is at least 1 point in C infinity in the completion of C, such that something strange is happening. And so we're going to analyze the situation near that point. Okay. Yeah, okay. So, yeah, so let's start the proof. So I already started the proof somehow. So FT algebraic family. So I'm saying, so this is non-isotrivial. So there exists exactly what I said here. There is some P in the completion of C, such that the class of FT tends to infinity in MD. And so what I'm going to do is I'm going to choose a holomorphic disk centered at P in C. So if you want a local holomorphic parametrization, so T is equal to 0 will correspond to the point P. And I'm going to work with this family now. Okay. So maybe, okay, don't be confused by the T here and T there. So I'm going to look at the holomorphic family now in a neighborhood of that point where I know that things are going to degenerate. Okay. So we have our non-Archimedean dynamical system, and we're going to look at its dynamics. So the first observation is that the topological entropy of this guy has to be positive. So remember, so why is it so? Because otherwise, so I explained yesterday, otherwise then there exists a holomorphic family of Möbius transformations such that phi t ft phi t minus 1 does actually converge to a rational map of degree d. Okay, but if this is the case, then if you look at the class map, this does not degenerate, right? So it contradicts my assumption here. So you have a non-trivial dynamical system. At least the Julia set of the non-Archimedean dynamical system cannot just be one point. Okay, good. But now so this is theorem by theorem 1. And I stated a second theorem, so on purpose. So here we use the assumption that this is isospectral. So isospectral, it implies that all periodic points of F and A are indifferent or attracting. I mean, for the t-adit norm. And so then we can apply theorem 2. And theorem 2 tells us that, good, so, but then the map is has to be Bernoulli. So F and A is what I call Bernoulli or piecewise linear. Okay. Yeah, classical, yeah. Always classical periodic points. Okay, so this means that the Julia set is inside the Julia set of F and A is inside a segment. So and the restriction of the map to that segment is piecewise affine. Let's say like this. Okay, so this is a segment inside the Julia inside the Berkovich space. And that contains the Julia set of my map. And so now I'm going to look at the intersection with the, so this is F, right? Or F and A. So here you have to understand that this segment is something of the form, the set of points of the form zeta 0, exponential s for s in between, I don't know, A and B, okay? So remember the formula in the case of the Macmillan family. So you didn't have three slopes, but only two. One was, I don't remember, -3, and the other one +2. Okay, I don't know why I wrote with the three slopes, but why not? Why not? Okay, so now you're looking at the intersection with diagonal. And as you see, you have, you have a lot of fixed points. So just take one, this one. And we're going to assume that, so up to reparametrization, we can always assume that the fixed point here is actually the Gauss point. so corresponding to the ball center 0 and radius 1. Okay, so so what we have, so f of xg is equal to xg. And remember that it was interesting to look at the action of f on the set of directions. And this action corresponds to, in fact, the reduction of the map. Okay? And so here, what I'm claiming is that, in fact, this map, this action on the set of direction, is controlled. So, in fact, it's a monomial map. So why is it so? It's because if you, so this is, you have 0, infinity, maybe the segment I is in here, and we are looking at the point xg. And so, I didn't think too much, but the Julia set is a counter set in here that contains xg. In fact, the Julia set is totally invariant, and so you can show that these two directions at xg, the one going to 0 and the one towards infinity, are totally invariant. So both directions at xg defined by 0 and infinity are totally invariant and fixed. And so I don't know many rational maps that have two totally invariant points that are fixed. It's necessarily, so this means that f tilde, or the tangent f, has to be x to some power delta. Okay? Okay, I use z as a f of z, is it delta? For some delta. What is this delta? So remember that the degree of the reduction map, in fact, is connected to the local topological degree. And here you can relate this to the slope that you see here. So it's exactly the slope of this blue line. So I don't know. Well, let me call it delta. So this is why it's at least 2. Okay? Okay, good. So now that we have that we have this non-argument information, we're trying to translate this to back to the complex. So let me, this is always the same stupid picture. So I'm going to look at what's happening near that point where things are degenerating. And so what I know is that, so I have a rational map of degree d of the central fiber. And on the central fiber, f tilde is the limit of the rational map, is z goes to z to the power delta. Okay, so you can argue a little bit, so there is a problem with the point of indeterminacy, but you can argue that in fact they are at 0, whoops, probably it's infinity and 0. And so for those you know, so why is it the case? It's because, so the point of indeterminacy here over the complex, you can spot them by looking at the pre-images of xg inside the Berkovich space, but since xg is inside the Julia set, they have to lie somewhere in the segment. So they have to be determined by 0 and infinity. Well, okay, fine. So so here what is interesting is that z to the power delta, the minimal map, has a Julia set. It's here. So, okay, so this circle, no. It's not so thin. So, okay, let me do, so the blue line is now a blue plane. And so you have 0, which is indeterminate. And then you have infinity, which is indeterminate, so things are degenerating in a bad way. But then you have this unit circle where you have a lot of periodic points. So you have a lot of periodic points whose multipliers are exactly equal to delta. Okay? Okay, and so then you're back to holomorphic dynamics. So what you see is that you have your monomial map is preserving that fantastic circle on which the dynamics is hyperbolic. And so it means that topologically you have a hyperbolic set nearby. Okay, so this hyperbolic set is going to be like a quasi-circle, which is going to be invariant by Ft. So you have a family of a circle that are invariant. And again, so the dynamics is going to be topologically conjugate to that one. And so you have a lot of periodic points. But we assume that family is isospectral. And so what you have is that plenty of parameters, well, in fact, all parameters nearby that have quasi-circle, which is invariant, and a lot of periodic points. And that's strange because all the periodic points have the same multipliers equal to delta. Okay? And so then you need to argue that this implies, okay, so let me write there. So there is a non-trivial but well-known argument that says that then Ft is in fact understood. So for T,
T1 upstream.
Exchange coordinates.
or T small, so you have, there exists, let's say, a gamma T quasar circle, which is invariant, and over which there exists a conjugacy to the map z goes to z to the power delta. Okay, and then the extra information is that plus all multipliers are constant, so are equal to delta. Okay, so then I'm not going to, so yeah, I have plenty of time, so I'd like to do something else, but so this is a very interesting part, but this is basically a theorem by Rit, and then it was exploited by Eremenko and Van Strien in their classification of rational map with only real multipliers. So this implies that in fact Ft is very rigid, so Ft is either monomial or Chebyshev or lattice. So not necessarily lattice, flexible lattice, but then you complete the proof by looking at, okay, but the being monomial is just an isolated point inside the modular space, Chebyshev the same, and then you have either flexible lattice or rigid lattice that are also isolated. Okay, so just one word about how you conclude the proof. What you do, in fact, is that you, I'm not going to do it very precisely, but so you look at a fixed point, so it has to be repeating on that quasi-circle, and then you look at the Poincaré, let's say, Q. You look at the Poincaré linearization, linearizing map. So it maps 0 to Q, and it conjugates the map Ft to the multiplication by delta. And then the claim of Rit is that if you have enough non-trivial symmetries for this linearizing map, then your map is exceptional, is integrable, is whatever, is in this list. So the statement is that if there exists a translation, non-trivial translation, let's say T, such that psi composed with T is equal to psi, then your map F is like that. Monomial, Chebyshev, lattice. And so the game is here is to try to construct that translation. And so the way you do that is, okay, so it's 15 minutes, so I'd like to do something else, but plus my hesitations. So But so what you do is that, so you look at the pre-image of that guy. So here, and you know that a pre-image by equidistribution, the pre-image, you're going to have a lot of pre-images close by here. Okay, and so you have a sequence of points, an inverse orbit, sorry, of points that of that guy that converge to itself. Then this means that if you take a small disk, then it grows under iteration, and then it's mapped to that big disk. And so you get a sequence of periodic points of higher and higher period that accumulate on that point. Okay. And then what you do is that you do some kind of rescaling, playing with this periodic orbit to construct these things. So you build a holomorphic map, and exploiting the fact that all multipliers are actually equal to the same number, you check that the derivative has to vanish too often, and so the derivative of t has to be no, it has to take the same constant, the same value at too many points, sorry. And so the derivative is going to be constant, and so it's affine. And then you need to do some extra work to actually produce not an affine transformation, but a non-trivial translation, okay? But okay, so read the paper by G and Chi. They have beautiful pictures. And so, yeah. But I think this is the main idea, okay? Okay, so I could stop here, but yeah, okay. But Matthias is here, is going to ask me things.
So could you just explain again for how you go from the tangent map to something inside a central fragment? It's exactly the same thing.
What did I say?
I mean, your argument was that you looked at a tangent map, you have two totally invariant directions, so that one's c to the delta. So you get something, you get a unit circle or something.
So you have to understand, so if you have a family, yeah, parameterized by unit disk, then you have to understand so when t is equal to 0, it turns out, so if it turns out to be a non-trivial rational map, you have to explain that this rational map is actually determine the action on the set of directions. And so I go back and forth from this information to, do you want to know, to explain more on this? Yeah, so yeah.
Go on, there will be a lot of questions at the end.
Oh, yeah. So I have to run out of this room very quickly. Okay, yeah, 15 minutes. Okay, so I had a long list of comments on so there are a lot of works on the functions, so the multiplier functions. So this statement, in fact, implies that if you look at the multiplier function, this is a finite to one map from the moduli space to a suitable affine space if you remove the flexible lattice family. And then people have proved, G and Chi have proved that this is actually injective on the Zariski open set. Silverman bound the degree, and then Valentin also is where is he? Here. So he had a lot of very interesting results about if this map is proper or not, and so on and so forth. So if you have questions about the multiplier function, ask me, and I will tell you to talk to Valentin, who knows everything. Okay. Okay, so what I'd like to do, though, is to talk a little bit about recent developments on how to extend this theory of degeneration of holomorphic families to degeneration of sequences. Okay, so what you have to understand is that if so the parameter space, as I said, of a moduli, the moduli space of rational map is not one-dimensional; it's 2D minus 2-dimensional. So you might be interested in looking at not only one parameter family, but 2, 3, 4, 2D minus 2 parameter families. And so then it's less clear how to cook up this recipe on how to attach to FT a non-Archimedean dynamical system. So I'll try, okay, in 15 minutes, so it's going to be quite quick, but to tell you how one can do that. Okay, so you start with now a sequence of rational map, fixed degree. And then I'm going always to assume that its class map is going to diverge in the moduli space. And what you want is to construct an Anakimian limit. So you want a rational map on some non-Akimian field of degree the same, d. So K is going to be non-Akimelian, complete field. And you want the, so I'm not going to explain what's going to be the relation between the two, but at least the dynamics, you want it to be non-trivial. And we understood that being non-trivial means the topological entropy is positive. And so FNA should not have potential good reduction. So you want this to be positive. So the Julia set being non-trivial. Okay, so so you have several approaches to this. So one is kind of, so you look at the space of all rational maps. It's affine. Now you try to compactify using hybrid constructions, and then you take points in the limit and so on. So this is an approach which is due to Toineau and his student Alexandrois. It's like hybrid compactification of MD. And then you have an approach by Yusheng Luo, and that we rephrased with Chen Gong using a little bit more of Berkovich theory. And so these two approaches are very similar, and they're based on ultra product constructions. So in the case of Yusheng, what he's doing is looking at a natural extension of the map. So if you want a rational map, it's a continuous map on the Riemann sphere. The Riemann sphere is the boundary of the hyperbolic 3 space, and then there is a way of extending this map non-trivially to the interior. And what it does is, so you fix a sequence of numbers, epsilon n, that tends to 0. And you can take some limits of this, pointed limits of this space in the sense of Gromov, and the limit is going to be an R3. And this R3 turns out to be an identification of P1 over some field, which is a bit mysterious. And so what we did was to somehow remove that part that extends you to hyperbolic 3 space and use more systematically Berkovich theory. So, so I have 10 minutes, so I'm not going to be very precise, but I'd like to explain to you a couple of things. At least, if I manage to define this field, that would be nice. Yeah, I should say that, so all this is, it has been known 40 years ago, or 40 years ago, in the context of Klein groups. So they're much better than us, I don't know. So this approach by Luo is in fact was in fact developed by Paulin and Besvena. And this approach that we follow is more or less the approach of Morgan and Challen. But it's really completely similar. And of course, then Berkovich was not in the place, so they don't use Berkovich spaces and so on, but it's essentially the same. At least the spirit is the same. Okay, so let's say the two keywords here are ultra blah and scales. Okay, so I need to explain to you. So I need to talk very briefly about ultra filters and why this is useful. So what is an ultra filter? Let's call it omega. So it's a collection of sets inside the set of integers. And if E is inside omega, you're going to say that this is omega big. If E is not inside omega, it's going to be omega small. So you have a list of axioms. So for instance, you want n to be big. You want finite set to be small. You want that if you're big and then you take someone bigger, then f is again big. If you have E and F that are both big, their intersection is big. So everything is quite natural. And the last one is if you take any set, E, then either E or its complement is big. So does it exist? Yes, if you believe in the axiom of choice. So if you don't believe in the axiom of choice, I don't know what to do. Anyway, so why this super useful is that you have, so if you take any compact set and you take any sequence in this compact set, then in fact, okay, so I choose once for all one non-principal ultrafilter, so again, it's satisfying this. Then you can define, then there exists an omega limit. So there exists a limit of x inside k along omega. So what this means is that, so let me call it, so lim omega of xn. So it satisfies the following for any open neighborhood of x infinity u. The set of integers such that xn belongs to u is omega b. And it's an exercise to prove that, so using a Borel-Lebesgue property, that this is actually true. Okay, so this gadget is very useful. So the sense that if you, for instance, take your sequence of rational map in RAD-D or MD, then it says if I fix omega, then I get a point in the boundary in any projective compactification. So the idea is that if you give me a point in the boundary in any projective compactification, that is, in fact, you're giving me some rational map over some non-Archimedean field. So this is what I'm going to explain. Okay, so the second ingredient is the notion of scale. As I said, so this is just a sequence of numbers inside 0, 1. And so you can, so if you want this scale, it's going to be the speed at which you're going to zoom in, such that to have your limit. Okay, so you have a notion of since we're working only along omega sequences, if you want. So you have a notion of equivalence of two scales. If they agree on an omega big set, then they're the same. In fact, a bit more if their quotient is bounded from above and from below. And you have a total order on the set of scales. And so the set of scales is kind of an interesting object, but I don't really need this right now. Okay, so now I can define my the ultra product. So it seems that I started a new talk and then going forever. Don't worry, I'm going to stop in 6 minutes. Okay. So so what I want to explain is what kind of non-Archimedean field are going to show up in these constructions. So you fix a scale, epsilon like this, and then you define h epsilon. So this is the set of all sequences in of complex sequences, of complex numbers, sorry, such that, okay, so you can look at Zn to the power epsilon n, okay, and I'm going to, so this is an element of R plus, sorry, and so I can take its limit. It's possibly infinity, but I'm going to take only those sequences for which this is finite, and you caution out by those sequences for which the limit along omega is equal to 0. Okay? Why not? So if you have, so what are the, so if you have two sequences, what is the sum? What is the product? Well, you sum and you take the product term by term. And you can check that this is, whoops. that this defines a ring. It's actually a field because you quotient out by the kernel here. And then you also have a natural function, which to a point, which is a sequence, you attach this limit. And this defines a norm. Okay. So observation. So this norm, as soon as epsilon n is converging to 0 along omega, then this norm is non-Archimedean. So epsilon n tends to 0. Well, okay. It's non-Archimedean. And when epsilon n is, let's say, the constant function, then you can check that epsilon, h epsilon, sorry, is in fact isometric to C with the standard norm. Okay, so now how do you define, I erased everything almost. So how do you define the limit here? Okay, so you fix your scale. So a priori, it's not clear which scale is going to be interesting. Okay, but let's take any scale. And then you write, so you choose homogeneous coordinates in P1, and you write Fn, you define by the pair of polynomials Pn, Qn with complex coefficients. And as usual, we're going to normalize the coefficients such that the maximum of the complex norm of A, I, N, B, J, N, so there are coefficients of P and Qn, is equal to 1. And so if you fix an index I or J, and you look at this sequence, this is a sequence of complex numbers inside the unit disk. So in particular, for any scale, it satisfies this condition, right? It's even bounded. So you can attach to this an element, let me call it AI epsilon, which is in H epsilon. So this thing here is exactly what we did for holomorphic, in the case of holomorphic families. So the coefficient in the case of holomorphic family, the coefficient were holomorphic functions inside on the unit disk. And we interpreted this holomorphic function as a new element in the field of formal power series. So here we're doing exactly the same, except that it's no longer a family, but now it's a sequence, and you interpret in this H epsilon. Okay, so you get a map with F epsilon, which is a rational map on H epsilon. Ooh la la. Okay, so this is the last statement. So now I have to explain a little bit what's happening. So you have a lot of possibilities for the scales, but the theorem is as follows. So, okay, let me. So you have some kind of critical scale. The critical scale is, so I don't have time to discuss this in details. It's 1 over minus log of the resultant of Fn. So remember, I defined the resultant. It's it's not well defined on RAT D, but if you normalize the coefficients and take the resultant, then this is well defined. And the resultant is going to 0 if your map is going to infinity in RAT D. Okay. So this, if you're degenerating in RAT D, this tends to 0. Yeah, I'm getting crazy about all these numbers, but so this tends to 0, then minus infinity plus infinity, 0. Okay, fine. So I'm going to conclude here. So if the scale epsilon is going much faster than this critical scale, then in fact what you get is that so degree of F epsilon is D, fine, but it has good reduction. If you're going too slow, slower than this, then the degree is strictly less than D. And if you're going right at the same, at the good speed, then it's almost true. So I'd like to write this is positive, except that what can happen is that, in fact, there is some kind of Fecht degenerations. Fn, let's say it's in the same conjugacy class, and then you're degenerating to infinity. But in fact, in the moduli space, you're not degenerating. And so here, what you want is that, so there is a slight twist here, is that you want Fn to realize the maximum here. So you want that the resultant of Fn is the supremum over, for any n, over any g in the same conjugacy class of the resultant of Gn. And so if this is true, so if Fn is somehow you choose Fn in the conjugacy class such that the resultant is maximal, then to degenerate in the moduli space implies the distance to 0. And then you can show that actually you have a positive entropy. And what is the non-Eichmann limit? Well, this is exactly that one F epsilon at that critical and I'm over time. So yeah, thank you.
Are there any questions? Yes. Ron?
Yes, if you have an isospectral sequence, we can use that.
Isospectral. What do you mean by isospectral? Yeah.
All the multipliers are the same.
Yeah, if the multiplier, if no multiplier is exploding, then you can, the limit is going to be Bernoulli. Yeah. Yeah, so if, but okay, not more, come on. Already a lot. So, so in this limit, it's just like for ft, you have a good connection between sequence of periodic points of Fn and periodic points of the limit. And the multiplier, what is the multiplier of the limit? It's an element in H epsilon, which is determined by the sequence of multipliers of the sequence. Okay, so yeah.
So the limits that you get when you're epsilon, so greater than epsilon f, okay, that means it shrinks less fast.
Yeah,
I mean,
yeah.
okay. And those limits are, did you say, are those corresponding to rescaling limits of the, or local
Sometimes.
booms of the?
So it could be that, so yeah, so we discussed yesterday, when that's also, I have an example to, so if you look at this very simple examples, so what was it? Exponential minus n z cubed plus z squared plus c. Let's start like this, okay? So, okay, well, okay. Let's say plus 1 over n, okay? And then I'm going to change, okay? So you see, it's strange, you have two different speeds. One is exponential, and one is, okay, or 1 over n, and the other one, when you take logs, it's a 1 over log n. Okay, so then the speed here that you have to take is epsilon is 1 over n. And the limit is going to be a cubic polynomial, okay? But if you take the speed, which is 1 over log n, it's going to kill that thing. So this is going to 0 much slower than this one. So it's going to kill this, and you're going to have to see z squared plus n, or, okay, sorry, yeah, z squared plus n. And so the limit is going to be z squared plus something above, with norm bigger than 1 over non-Euclidean field. And sometimes, so if you, if you replace n by your favorite, calm down, okay. So by any complex numbers, then if you can look at the degeneration at speed 1, and then you get a standard rescaling, a complex rescaling limit in the sense of Yan Q, okay, which is z squared plus c. Okay, so yes, there is, and you can play this game. So this is our last paper of trying to understand all the interesting limits. So you take a sequence, try to find all the limits everywhere, either over C or a non-Euclidean field of this sort. And yeah.
Any more questions?
People looked at this rigidity theorem if you don't assume it's an algebraic family, just a good question. It's not, nothing is known. I don't know.
Stable is not equivalent to isospectral first.
Okay.
But if you look at isospectral spectral, maybe you can show directly that
It's spectral proof, not stable, right?
Yeah, but as a spectral would be.
will be algebraic in the end, so maybe it's automatic. I don't know. Yeah.
So you could remove algebraic from the
Yeah, I
statement.
guess so. Yeah.
I think so.
A posteriori, I think you can remove it.
I think so.
Yeah. If you just, yeah,
It's not a bit weird.
you're right.
But you cannot, so again, you cannot just assume that the multiplier are bounded. This is main thing. It has to be constant.
Okay, if there are no more questions, let's then start again from